we had started yesterday talking about interference. You actually plotted interference graphically. And now we're going to talk a little bit about reflection. So you saw reflection in pulse waves when you sent a pulse to your friend and it came back. When we were out in the hall yesterday with the big spring, I could send a wave at Jason, he could send a wave back to me. But did it just stop when it got to me? No. It actually reflects back through the medium. And this is how you get, and again, I don't have my overhead projector to do my ripple tank, but when you drop something into a pond, those ripples travel out to the edges of the pond, and then they reflect back. So they end up interfering with themselves, which makes it all the more complicated and beautiful. But reflection happens in two different ways. So you have free boundary reflection and fixed boundary reflection. And let's actually take the big spring out in the hall and try this. We're going to do a lot of, let's go out with the spring, let's come back, let's talk about it, let's go out with the spring, let's come back, let's talk about it today. It's going to be that kind of day. So when you have that free end, the wave comes back in the same pattern you saw it travel down in. So in that case, we can say it was up. So the reflection came back sort of above the equilibrium position. Guess what the case is for a fixed end? You get an inverted reflection. That's the big difference. With a fixed end, you get the inverted reflection. With a free end, you get an identical reflection. Not all that hard. Something that you can memorize. You can also play with something like the string software. Or you can go out and get some big washers and a pole, sink it in the front yard, grab a rope and get all of your little 8-year-old cousins and tell them you have a game for them, which could provide for an entertaining Saturday afternoon, perhaps. Okay. Now we get to the really fun part. Standing waves. So this is one where you end up with reflections coming back and interfering. So this happens when you have a simple harmonic motion creating a waveform. So you have a wave pattern, and the reflections of the wave pattern interfere with the oncoming wave. So basically you have your original wave traveling this way, your reflected wave traveling that way, or another wave traveling that way. And what you end up with is a pattern that doesn't move on the string. And you create a standing wave. So, okay, let's head out and take the big spring, and we can definitely get standing waves going. That point you saw where it appeared that the wave was not moving at all, that's an area of total destructive interference. So the waveforms are actually canceling one another out. We call it a node. And at a node, the medium is actually not moving. So you've got a point where it just stands still. Now, the opposite of that are the antinodes. And the antinodes are areas of constructive interference, and that's where you have maximum motion. So you have maximum constructive interference. It's total constructive, and you get this really neat pattern. And you probably actually saw this shape in the spring out there, did you? From the side? Okay. Let's talk a little bit about standing waves, wavelength, and the pattern of nodes and antinodes. So I'm going to do my my normal best worst drawing of a standing wave. Let's actually do that first standing wave you saw. You get the idea. So Here's your area of total destructive interference. What's that called? Node. So that's your node, that's your destructive interference. I guarantee I will screw that up at some point. I do it every single year. You have this area of constructive interference where the amplitude of the wave is greatest. What's that called? Antinode. Antinode, antinode. We're not in Kansas anymore. Where's the wavelength here? So let's label a few points. A, B, C, D, E. From what point to what point gives you a wavelength? A to E. Reason being, you have to go through an entire cycle of motion to achieve wavelength. So let me get one more color to highlight here. So here, we start at equilibrium, we go through maximum amplitude, we go back through equilibrium, we have to go through the other side of maximum equilibrium before we have a full wavelength. Okay? And I ask that because the most, generally about half of physics students, when I ask that question the first time will say, oh, A to C, but that's not a wavelength. That's a half a wavelength. So there's a neat little pattern to these things. Okay. So, in a standing wave, every single point on that string is vibrating at the same frequency. The amplitude is different. There's one, well, there can be one or two, well, 2 or 4 or 3 points that aren't vibrating at all, and those are the nodes. The nodes literally do not move in a true standing wave. They are totally stationary. There's no vibration, there's no oscillation. If we look at the first, this is called the first harmonic, and we're going to go through the harmonic sequence. The point in the string here has a different amplitude than a point here. Your greatest amplitude is at the antinode. Yes, sir? No, nodes are the points of no motion. Antinodes are the points of motion, maximum motion. Okay, so if we look at this first case, this first harmonic, how many nodes are there? Where are the points where the string is not moving? 2. They're on the ends. Node 1, node 2. In the second harmonic, how many nodes are there? 3. 1, 2, 3. In the third harmonic, how many nodes are there? 1, 2, 3, 4. That's the harmonics. So n equals first harmonic, second harmonic, third harmonic, not nodes equal. Okay, yeah, fourth harmonic. 1, 2, 3, 4, 5. So there you can have a 20th harmonic with 20 points on a string that aren't vibrating. In harmonics on a string, yes. And we're not going to get to do pipes. Open and closed pipes have different kinds of harmonics. But we're sticking with strings because I wish we could do the sound unit. Does that make sense, Zach?
Yeah, I was just
okay.
Confusing.
That's exactly what I do.
On either side of equilibrium.
That's exactly what I do. Yep. I do it all the time. I do it every year. So
Does it mean nodes?
But you can have a whole bunch of different standing waves on a single string. And you could, how many good standing waves did we actually get on the spring out in the hallway? 2. I think we definitely got 2 going well. Did we get a third going? It's hard to tell from the ends.
I think I saw 4. I saw 4.
You saw 4? Okay. Well, meaning you saw 4 antinodes? Okay, but I think we got at least 3 different standing waves going. We had one that had 2 antinodes. I know we had one that had the 4 antinodes. Did we have a 3 antinode for a little while? A third harmonic? Okay. A jump rope, actually, is the first harmonic. So But that's hard to get going with a spring like that because you don't actually want it to be going like this. You just want it to do this. So you can get multiple standing waves out of the same length of string or spring or whatever. But there are only certain frequencies that will actually create a standing wave. So, I had to play around and Claire had to play around with how fast we were moving that string. Let's attempt this on the string program. This last point. That only certain frequencies on a given length of string will create a standing wave. Okay. This is what I said, where you can't have a standing wave on a string with less than 2 nodes. It's different in an open pipe. Tomas, you're saxophone, right? Okay, and Skylar's, is she also wood? No, she's brass, I knew that. Zach, are you brass or are you percussion? You're brass, okay. So both, a trumpet, a tuba, a baritone, a trombone, a saxophone, a clarinet, all of those are closed on one end pipe systems, and there's a harmonic series, and you change the length of the pipe by opening and shutting valves. So, again, we don't get to do the music unit. I'm sad, but there are only certain patterns of vibration that are possible. In a pipe, we can have open ends. On a string, we have to have fixed boundaries, or we can't create a standing wave. The wavelengths possible for any standing wave are multiples of the length of the string itself. So if we have a string, and I'm going to put my string here, and this gets back to what is the first standing wave we can generate? Well, it's that. That was terribly drawn. And I sort of do this like rainbow thing. Well, what's the wavelength here? Am I showing a wavelength here? What's the wavelength of this standing wave? So here is the length of the string. Do I have a complete wavelength? No, I don't. Because to get a complete wavelength, remember, I would have to go through one entire cycle of motion. So the wavelength for the first harmonic is actually 2 times the length of the string. So we very often show this, well, there are a couple ways to do it. We can show lambda 1, which just stands for the wavelength of the first harmonic, and that's always equal to 2L. So if we have a 3-meter string, what is the wavelength of the first harmonic? 6 meters. It's a long wave. It's a very long wave. Well, I'm going to shrink this. Actually, I'm going to get rid of, whoops, get rid of this, and then shrink all this. So let's look at the second harmonic on that same string. Whoops, string only goes to there. So we have 3 nodes, 2 antinodes. What's the wavelength relationship to the length of the string? So lambda 2, yeah, it's equal to the length because we're actually going through one full cycle of motion. So lambda 2 is equal to the length of the string. The ones where it gets a little bit trickier, and I'm going to draw this larger and because I always screw this one up. And I'll shrink it down as I need to. Okay, so for the third harmonic, if I look at lambda 3. What's the wavelength of this standing wave? 2/3. And there's a really simple relationship with the number of antinodes that you see. Because a wavelength is always going to be how many antinodes? 2. Because you have to go through that entire cycle of motion. So here you have 3 antinodes. Lambda 3 equals 2/3 L. Move these up and shrink.
Did you say wavelength is always 2 antinodes?
Why? Or did I? Yeah. A wavelength has always got to be 2 antinodes. Well, and if you look at the first harmonic, you only have 1 antinode, which means the wavelength is actually twice the length of the string. In the second, you only have 2 antinodes. The wavelength is the total length of the string. Here, it's 2/3 the length of the string because you have 3 antinodes. So if you were a betting person, I'm really terrible at drawing these larger waveforms. So the wavelength for the 4th harmonic would be what? 1/2, because it's 2/4. It's 2/4 or 1/2 of L. So, for the 5th harmonic, oh boy, this is going to be awful. 1, 2, 3, 4, 5. There we go. Okay, it's pretty ugly, but we'll take it. Wavelength for the 5th harmonic? 2/5. Without even drawing it, what would be the wavelength for the 6th harmonic? It'd be 2/6 or 1/3 L. Okay, and this is actually, I mean, a guitar string is vibrating like this. You're creating harmonics on a guitar string. Okay, so additional homework problems assigned today. Tomorrow, FIP quiz while I'm out testing the biology peoples, and that'll be on wave interference and harmonics and string length. That's it. Okay, so these are the problems that are added to the homework. The homework will all be due on Thursday, the 12D homework. And so FIP tomorrow, 12D homework, and then test on Friday. So a lot of conceptual in this chapter.